Yes, it's Uncle Jegs, and today we're looking at the resistance required practical. First I'll touch on what electricity is, then I'll look at what resistant means in terms of electricity. We'll then have a look at series and parallel circuits before we're ready for the required practical. As always, check out the description for today's worksheet and also the answers to the previous video's worksheet. Alright, let's keep that thing. Electricity is a little different from what we intuitively think it is. It really isn't actually a thing per se, it's a process. When a charged particle moves around, that is an electric current. The current isn't the charged particle itself, it is the movement of that charged particle. And it can't be just any old particle, it has to be charged, yeah? We use metals to transfer electricity because of their structure. A metallic structure is made up of metal cations and delocalized electrons. Remember that cations are positively charged particles. These electrons, as I said, are delocalized, which means that they don't stick to one location, they literally get around. The electrons are negatively charged, so if we can get all of them moving in the same direction, we can cause an electric current to flow through the wire. Current is measured in amps. This is the amount of charge that passes a point in a second. So if you have a current of 5 amps, that essentially means you have 5 units of charge passing a point in that second. The unit for charge is coulombs. So another way of saying 5 amps is 5 coulombs per second. But the electrons in a wire are all moving in random directions, so when there is no current there, you can't do any work. So some of you have probably clocked what we need to do. We need to add a battery or a power pack to get our electrons moving in the same direction. If you look closely at a battery, you see a number next to the letter V. This tells you the potential difference that battery can provide. One end of the battery has a high electrical potential and the other side has a low electrical potential. Since we have a difference in electrical potential, we say that we have a potential difference. The electrons are dying to move from the high potential to the low potential. All they need to do this is a path, and conductors like metals provide a path for them. The greater the potential difference, the more energy each electron can transfer to the components in your circuit. Therefore, if I have 2 circuits, one with a 1.5 volt battery and the other with a 3 volt battery, the first one can transfer just about half the amount of energy to the components. If this was a bulb, it will mean that the bulb is a little bit dimmer in the 1.5 volt circuit than in the 3 volt circuit. Cool. So our electrons are moving through our wire, but remember that we have large metal cations also within our metallic structure. And remember that the particles in solids aren't just jamming, they vibrate. The potential difference causes the electrons to flow in one direction, but these electrons collide with the metal cations. This means that there is some resistance to the flow of our electrons. This is like when you're trying to get to lunch from your classroom and you have to go through a crowded corridor. You bump into other students and that slows you down. And if you were an electron, the slower you move, the lower your current. Because remember, current is the amount of electrons flowing past a point per second. There are several things that can affect the electrical resistance of a wire. Sticking to the lunchtime analogy, if the distance between your fantastic science lesson and the canteen is short, you will go through less students in the corridor and are therefore less likely to bump into these students. This means that you can move faster, so there will be a higher current. The shorter the path, the lower the resistance. In the context of the wire, the longer the wire, the higher the resistance. This means that the likelihood of hitting the metal cations increases as the length of the wire increases. The second is the width of the wire. If you shrink the width of one of these corridors, you will have some next level of resistance. In a wider corridor, you will experience less resistance. So in the context of a wire, the wider or thicker the wire, the lower the resistance. I'll leave you with this puzzle to figure out. What do you think happens to the resistance of a wire as I increase the temperature of the wire? Would the resistance increase, decrease, or stay the same? Have a go and then check the comment section for the answer. You are also expected to be able to calculate resistance from your potential difference and the current. You get the potential difference from your voltmeter and the current from your ammeter. The equation is resistance equals potential difference divided by current. In your equation triangle, that is the potential difference at the top and the resistance and current are both at the bottom. That means that current is potential difference divided by resistance, and potential difference is resistance times current. Alright, quick summary. Current is the amount of charge passing a point per second, and we measure this in amps. Potential difference is the amount of energy transferred by the electrons, and this is measured in volts. Resistance is the opposition to the flow of a current, and we measure this one in ohms. You have two types of circuits. Series circuits only have one loop of wire that goes through your components. Since there is the same number of electrons going through that single loop of wire, the current is the same everywhere. The potential difference in a series circuit is the sum of the potential difference of your cell in the circuit. So for example, using a 3-volt battery in this circuit would mean that the two bulbs, if both of them have the same resistance, will have a potential difference of 1.5 volts across them. It's a little different with parallel circuits though. These have multiple branches. The total current through the whole circuit is the sum of the going through the separate branches. The current in the main branch here is 0.3 amps, and this is split between the two branches. However, the potential difference is the same across each component. Have a think about the type of circuit you would want to use for Christmas lights. Okay, it's time for the practical. This practical is broken into two activities. You will investigate how the resistance of a wire varies with its length, and also investigate resistors in series and parallel circuits. For the first activity, you connect a wire from your power pack to your ammeter. Then from the ammeter you connect the wire to your first crocodile clip. You connect this crocodile clip to the zero end of your meter ruler with the resistant wire running through the middle. Then from the other end of your power pack, you connect a wire to another crocodile clip and you attach this to the other end on the 10 centimeter mark on your ruler. You then connect your voltmeter parallel to your resistance wire. You do this by branching two new wires from the wires with your crocodile clips and attaching them to your voltmeter. Switch on your power pack and record the length of the wire between the crocodile clip, the amps, and also the voltage. You then repeat this by moving the crocodile clip in 10 centimeter intervals until you've reached a final reading of 1 meter. So you should have 10 readings. You can then work out your resistance for each distance by dividing your potential difference by your current. Finally, you then need to draw a graph with resistance on the y-axis and the length of your wire on your x-axis. You should draw a straight line of best fit from your results. For the second activity, you start off by connecting a power pack in series to a switch, 2 resistors, and an ammeter. Then you connect a voltmeter parallel to your 2 resistors. Switch on your power pack and record the current and the potential difference. Then you rearrange your circuit so that the resistors are parallel to each other. Switch on your power pack and record the current and potential difference again. Now you simply calculate the total resistance for both circuits. You should be able to find this out about your series circuit. The total resistance of 2 or more components in a series circuit is equal to the sum of the resistance of each component. And for your parallel circuit, you should find out that the total resistance of 2 or more components in parallel is less than the resistance of the resistor with the least resistance. And that, ladies and gentlemen, them is it for this video. Check out the work in the description, and if you're still baffed, use the timestamps to skip to what you need to. Like, comment, bell and all that jazz, and don't forget that science is more than just a body of knowledge. More importantly, it's a way of thinking. Think big, in a bit.